Okay, today we're going to move into Chapter 7, Section 1 on radical expressions. This entire chapter is on radicals, which you may formerly known as square roots. We're going to talk about square roots, cube roots, fourth roots, and so on. And we'll get into much stuff with that. The good news about this chapter is, for those of you that were having some trouble with factoring, there is not as much factoring in here. So you can kind of think of this as a new start. I wouldn't say that it's much easier. It's just different. It's just a different chapter. And just as I say that, we'll move into our warm-ups, which is all on factoring. So go ahead and pause the video and see how you can do here. Okay, go ahead and see how you did. The only problem here that might be a little different than what we have seen before is the factor tree that we did in number 1. The factor are just a straight up number. So you just do a factor tree on it, and that's something that we'll be doing in this chapter. Okay, there's a lot I want to explain here about square root. You may have had some misconceptions about what you think about it, so I just want to clear those up right now. The definition of a square root, it's a number that, the square root of a number A, it's a number C, such that when you multiply C by itself, you get A. So for instance, the square root of 25, it ends up being 5 because 5 times 5 gives you 25. Every positive real number has two real number square roots, so we could also say 25 has a square root of negative 5 because negative 5 times negative 5 gives you 25. However, whenever you're evaluating the square root of 25, you're only going to call it 5 because that's called our principal square root. So when you're simplifying a square root, you're only going to consider the principal square root, which is the non-negative number of the two. Okay, so anytime you take the square root of a number, there are two square roots, but we only declare the positive one because that's called the principal square root. Negative numbers do not have real number square roots because you can't multiply something by itself to give you a negative number. So negative 16, for instance, does not have a square root because there's no number C such that C squared gives you negative 16. There is an imaginary number, and we'll get to that later in the chapter, that does allow you to take the square root of a negative, but for now you can't do that. Here's some notation. All of these radicals that we're going to be working with, this symbol here is called the radical. Whatever is underneath the radical is called the radicand, and whatever this little number is inside this portion is called the index. So right here, there's no number written inside, and when there's no number written inside, it's assumed to be a 2. So the square root doesn't have a number written for the index, it's assumed to be a 2. So here's the square root of 25, index 2, radicand 25. Here's the cube root of 8, it's pronounced the cube root of 8, the index is 3, and the radicand is 8. This is the fourth root of 81, 4 is the index, 81 is the radicand. This basically means since the index is 2, what times itself gives you 25? 5. Here, what times itself 3 times gives you 8? 2, because 2 times 2 times 2 gives you 8. What times itself 4 times gives you 81? 3. 3 times 3 times 3 times 3 gives you 81. Now, like I said, down here we only consider the principal square root. When you're simplifying an expression, you only consider the principal square root. But if you were to be solving an equation, such as this one here, which we're going to be doing more of later, you would consider both the positive and the negative because both of these numbers, when you plug them in for x, they both work. But for the first 4 sections here, 4 or 5 sections of Chapter 7, we are only going to have algebraic expressions. So only consider the principal square root. You will see this list of perfect squares and perfect cubes on the back of your packet, the very last page. You should familiarize yourself with all of these numbers and be able to recognize them. I think the first 25 perfect squares are there. So 1's a perfect square because 1 squared is 1. 4 is a perfect square because 2 squared is 4. 9's a perfect square because 3 squared is 9, and so on. Perfect cubes, 1 cubed is 1, 2 cubed is 8, and so on. You got your perfect fourths and your perfect fifths. You should familiarize yourself with all of those and be able to recognize them so that when you see a number like 343, you should be able to recognize that as a perfect cube, which is 7 cubed. So the cube root of 343 is 7. Okay, example 1. Square root of 25. What times itself gives you 25? 5. We only consider the principal square root, not the negative 5. Another way to look at this is going to help you for what we're going to be doing, especially when we start getting variables involved. If we did a factor tree on 25, we would get 5 times 5. Since my index is 2, I would need 2 of the same factor in order to pull it out from underneath the radical. Since I have 2 of these 5s, I can pull it out, and you're left with nothing underneath, so you would get 5. Just another way to look at it, and we will be utilizing that a lot. Something like letter B, you would only focus on the square root of 64 first, and then you would apply the negative. So the square root of 64, what times itself gives you 64? 8, and then you apply the negative, you get negative 8. When you have a fraction, since we multiply fractions straight across, we can just take the square root of the top and the square root of the bottom. You end up getting 5/8. Letter D with the decimal, what times itself gives you 0.0049. It ends up being 0.07. And just to show you, to remind you how to multiply decimals, I would do the multiplication. I get 49, 7 times 7. And then there's a total of 1, 2, 3, 4 decimal places moved. So I would have to move this decimal 1, 2, 3, 4 to get back to what I started at, which was this 0.0049. And what times itself gives you negative 9? Well, nothing. You cannot take the square root of a negative number, at least not yet. So we'll say, for now, cannot be simplified. I want to discuss using absolute value brackets. Here is something that's always true. When you're squaring a square root, this square cancels out the square root since the index matches up with the exponent and you're just left with a. However, whenever you have that exponent underneath, it's not always true. You may have to utilize absolute value brackets. The square root of a squared is not just a. And let me go through this little example here to illustrate to you. Let's plug 5 in for a, for the square root of a squared, and see what we get. And then we'll plug negative 5 in and see what we get. So when I plug 5 in, 5 squared is 25, square root of 25 is 5, so it did work there. However, over here, when I plug negative 5 in, I still get 25, square root of 25, which is 5. These do not match up. No good. So if I put these in, if I were to put both of these in absolute value brackets, then they would both work out. So the rule here is anytime this index, which since this index is even, since it's a 2, anytime the index is even, you are going to utilize absolute value brackets. So you see how we had a 2 here. A squared is the same as a times a. Since my index is 2, I need 2 of the same factor to occur, or the same factor to occur twice for me to pull it out. So I can pull out an a, as I did, but whatever I pull out has to go in absolute value brackets. Looking at another example, like the 4th root of a to the 7th, the shortcut way of doing this is you divide the index into the exponent. 4 goes into 7 one time with the remainder of 3. So 4 goes into 7 one time with the remainder of 3. 3 of them are left over underneath the 4th root. But remember, since my index is even, whatever I bring out of the radical goes into absolute value brackets. Another way to look at it, if I actually were to write out a to the 7th, I know this way is a little bit longer, but it might be better for some of you to understand. If I wrote out a to the 7th as a times itself 7 times, since my index is 4, I now need 4 of these in order to bring one out, and it just becomes one of these a's. But since the index is even, I put it into absolute value brackets, whatever I bring out, and then I'm still left with 3 of them underneath. So you get the same thing, just a different way to look at it. Anytime the index is odd, like a cube root or a 5th root or a 7th root, you never need absolute value brackets. In fact, you do not use them. Okay, looking at example 2, we have a couple problems to look through here. Easiest way to do something like letter A, my index is 2. How many times does 2 go into 2? One time, so I can pull out one of those negative 16s. However, since my index was even, whatever I pull out has to go into absolute value brackets. The absolute value of negative 16 we know is 16. Another way to look at this one, since we actually know what negative 16 squared is, I can call this square root of 256. What times itself gives you 256? 16. So that's why you want to be familiar with your perfect squares. Know that list. Something like letter B, my index is 2. How many times does 2 go into 2? One time. So I can pull out one of those 3 B's, put it in absolute value brackets. We already know what the absolute value of 3 is. It's 3, so that can come out. And then we don't know what B is, so we need to keep that in absolute value brackets. Letter C, how many times does 4 go into 6? One time, with 1 left over, or with 2 left over rather, remainder 2. So I leave 2 of these x minus 1s underneath the radical, still a fourth root. And the x minus 1, since it was an even index, has to go into absolute value brackets. And finally, letter D, we do have some factoring to do in this chapter. So this factors to x plus 4 squared. Now I can use my rule, divide my index into the exponent. How many times does 2 go into 2? One time. I can bring out one of those x plus 4s, and it goes into absolute value brackets. Okay, go ahead and try, pause here and try these checkpoints. Okay, go ahead and see how you did on these. And we'll move on to cube root. Now cube root is when the index is 3. Here's an example. 2 is the cube root of 8, because 2 times itself 3 times is 8. And you can't take the cube root of a negative number. So the cube root of negative 125 ends up being negative 5, because negative 5 times itself 3 times is negative 125. You're never going to use absolute value brackets since the index is odd. Cube root of 216, what times itself? 3 times gives you 216. 6. What times itself? 3 times gives you negative 64. Negative 4. Same thing here. Cube root of the top and the bottom, you end up getting negative 7/3, because negative 7/3 times negative 7/3 times negative 7/3 gives you negative 343 over 27. Take each piece at a time here. Cube root of negative 8 is negative 2. Cube root of y cubed, 3 goes into 3 one time with none left over, so you can bring out one of those y's. No absolute value brackets needed. Just to present you guys with another option here, this is going to help all of you. Even if you know that 216 is a perfect cube, you might get a number big enough that you might not know, so you might have to do a factor tree on it. So if you did a factor tree on 216, you would no matter how you started the factor tree, you're always going to end the same way. In this case, we end with 3 2s and 3 3s. Since our index is 3, we need the same factor to occur 3 times. So we have 3 2s, we can pull that out from the radical. We also have 3 3s, we can pull that out from the radical. There's nothing left underneath the radical. 2 times 3 gives you 6. So this is a longer way of doing it, but it also works. If you did know your list of perfect cubes, you can save a lot of time. Okay, this example here is just going to give us some practice on going into exponential notation. Takes us from radical notation to exponential notation. Right here, 5 equals the square root of 25. This is radical notation because we have a radical. If I wanted to get rid of the radical, which we are eventually going to want to do, I'm just going to take both sides to the power of the index. So here my index is 2. So if I square both sides, here I'm just left with 5 squared. And then since my index was 2 and I squared it, that cancels all of this out, and I'm just left with 25. So there's your exponential notation. Notice the word in exponential is exponent. We're using an exponent. So here, if I took both sides to the 7th power, I would be left with c to the 7th equals b, and that's exponential notation. And the final two. Okay, check to see how you did there. And the last thing we will discuss is odd roots and even roots. Basically, I already addressed this. If you have an odd index, then you'll never use absolute value brackets. If you have an even index, then you're going to use an absolute value brackets for whatever you pull out. So up here, k goes into k one time. That means you can pull out one of these a's. It would go into absolute value brackets if k is even. Otherwise, no absolute value brackets are to be used. Fifth root of negative 32. We can take the fifth root of a negative number because 5 is odd. What times itself 5 times gives you negative 32? Well, negative 2. Same thing here. However, we're going to hold off on the negative. Let's just find what the fifth root of 32 is. What times itself 5 times gives you 32? 2 does. And then you apply the negative. So in this case, you get negative 2 again. Here, 7 goes into 7 one time. Pull out one of the x's. No absolute value brackets needed. Here we have some even roots. Same idea. 4th root of 16 is 2, because 2 to the 4th is 16. Then you apply the negative. What times itself 4 times is 16. This is just 2. 4th root of 81 times the 4th root of x to the 4th. 4th root of 81 is just 3, because 3 times itself 4 times is 81. 4 goes into 4 one time. So I can pull out one of those x's. Since my index is even, I have to put that x in absolute value brackets. 6 goes into 6 one time. Pull out one of those y plus 7s, and it has to go into absolute value brackets. Okay, why don't you pause the video here and work on those checkpoints. Check back to see how you did. Okay, go ahead and check to see how you did. And finally, the closing questions. Okay, check your answers to those closing questions. And your homework is going to be the next worksheet in your packet, numbers 1 through 18 all.